We're going to finish up Chapter 9 by talking about two types of collisions. One is called an inelastic collision, the other is an elastic collision. Inelastic collisions are when two objects come together and they're going to stick together. Okay, so one object's going to come in, it's going to stick to the other object, and they're going to continue to travel. Or, one of the most powerful examples that they use over and over again, don't ask me why they choose to do this, is a grenade. A grenade exploding, because it started out as all the pieces were together, and then all the pieces were no longer together. Now these types of problems, we have to be very careful when we're solving them. The only thing that is conserved in an inelastic collision is momentum. Momentum is conserved. Okay? So this is the only thing that we can use to solve an inelastic collision. Momentum is conserved. The reason energy is not conserved, okay, let's think about the grenade for a second. When the grenade explodes, it started out with no mechanical energy. There was chemical energy inside of the grenade that gives it the kinetic energy afterward, but we can't model that effectively, all right? We're talking about basic Newtonian mechanics right now. We're not talking about chemical reactions. So this object started out with no energy, and then all the pieces are flying off in different directions with energy. Okay, so we technically created energy because we're not looking at the chemical reactions inside of the grenade. So we can't use energy conservation for that type of problem. Also, when two objects stick together, one object's coming in, it strikes the other object, and they're going to continue to travel. These two objects are going to rub up against each other as they're moving, okay? They're interacting with each other. Those tiny little interactions that they're having with each other are going to create friction. How do we model the friction that is going to result in energy loss? We don't really have a way of doing that. So whenever objects stick together, or when they started out as one piece and then it explodes into many different pieces, we're going to rely on momentum conservation, and this is what is called an inelastic collision. Okay? So, knowing that momentum is conserved, this immediately allows us to start solving problems. Let's have a 3 kilogram mass, and it's traveling with a velocity of 5 meters per second, and let's put it in the x direction, so that's why I used an I hat right there. It is going to strike a 1 kilogram mass that is initially at rest. The 1 kilogram mass is initially at rest. These two objects are then going to move together in some direction. And we want to find the final velocity of that movement. It's not 0, it should be question marks. We're trying to find that velocity of that final movement. Now looking here, right here, we know that the velocity is along the x direction. So that must mean that the final velocity is also along the x direction. Be careful. These problems can get really, really complicated if I start giving them to you in 2 and 3 dimensions. Then you need to do momentum conservation in the y direction and momentum conservation in the z direction. Here, I've done an example where all the motion is confined to the x-axis, so we can keep everything in terms of the x velocity. Okay? Now we know that momentum is conserved. So it starts looking like an energy conservation problem, but we're not dealing with energy conservation here. So the momentum initial must be equal to the momentum final. Now notice I've put the little arrows above the two momentums, momentum initial, momentum final. Notice I put arrows above them because the direction does matter. The direction does matter. You can have a negative momentum because it is a vector quantity. A negative momentum in this case, if we're confining all motion to the x-axis, would be a momentum moving toward the Hateful Eight poster, which we said at the beginning of the class was the negative x direction. Okay. So the momentum initial, all the momentum initially is inside this guy. The 3 kilograms multiplied by 5 meters per second. So 3 kilograms multiplied by 5 meters per second. He had all the momentum at the start. This guy's momentum is 0. Velocity of 0 multiplied by 1 kilogram, 0 momentum. Now when the two objects stick together, this is our train cars argument that we've been making since the beginning of the year. These two objects are stuck together, so they must have the same velocity, otherwise they would begin to separate. Since they have the same velocity, that means that I could have the first mass, the 3 kilograms, multiplied by the final velocity, plus the 1 kilogram times the final velocity. So that means here I've got 3 times 5, which is 15. I can combine these two guys as a total mass of 4. So it's 4 multiplied by the final velocity. And I get that the final velocity of these two objects is 3.75 meters per second. What's really nice about these problems is you can go back and check them to see if you did in fact have momentum conservation. 3 times 5 is 15. 4 multiplied by 3.75 is also 15. So we got momentum conservation in this case. All right? Now, classic problem that they're probably going to give you on the AP in some form or another is the ballistic pendulum. And boy howdy, doesn't this sound like fun? The ballistic pendulum. This is the old way that they used to measure the velocity of a bullet coming out of a gun. All right? Because they didn't want to have somebody sitting there with a ruler and a stopwatch saying fire, because that's a real easy way to have some kind of lawsuit in your future. So instead what they used to do is they used to set up this really funky looking apparatus. So what they'd do is they'd have a block hanging from some string, and in our case the block is 5 kilograms. The bullet is going to be fired, and it's going to come in, and it's going to strike the 5 kilogram block. Now the bullet has a very, very small mass. In this case, we're going to have a 2 gram bullet. And the bullet is coming in with some initial velocity that we don't know. Okay? Now when the bullet hits the block, these strings are going to allow the bullet and block system, when the bullet gets lodged inside the block, to swing upward to some height. So now I have the 5 kilogram block with the bullet inside. The bullet is inside of this thing. It swings up, and so now I have a height difference between where it started and where it ended. Okay? So the bullet has an initial velocity. We don't know what it is. The bullet has a mass, 2 grams. It's going to strike the 5 kilogram mass block. It's going to become lodged inside of the block, and the bullet and block are going to swing upward. We're going to work backwards to figure out what is the initial velocity of the bullet. Now be careful. I'm combining 2 types of arguments here. I'm going to do an energy conservation problem and a momentum conservation problem. Okay? And I'm going to work backwards here. I would advise you right now to pause this video and try this problem on your own, but I'm going to work through the solution right now. But I highly recommend you try this. If I was right now with you guys in class, I'd give you about 15 minutes to try this thing. Okay? Now think about what happens here. The bullet and block swing upward, and so now they are above where they start. What kind of energy do they have? They have potential energy, gravitational potential energy. So the energy right now is gravitational potential energy. Okay? So that's going to be mgh is our starting energy. Just as the bullet became lodged inside the block, we had kinetic energy inside the bullet and the block. Kinetic energy combined. Okay? So the energy was kinetic energy, and then it became potential energy as this thing swung upward and it stopped. This was a lot like one of your test problems from the last chapter. Okay? So the potential energy, we have the bullet and the block combined, 5 kilograms plus 0.002 kilograms. 0.002 kilograms is 2 grams. That multiplied by 9.8 multiplied by the height, 5 centimeters. Be careful with the unit conversion there, 0.05 meters. That's equal to 1/2 the mass of the bullet and block, 5 plus 0.002 times the velocity squared. Okay? So I'm using energy conservation to find out what was the velocity of the bullet and the block when they began to swing. And I get that the velocity was 0.99 meters per second. So that was the velocity of the bullet and block at the beginning of the swing. Now some of you guys are going to want to just go all the way to energy conservation here for the bullet. And you're going to say, okay, well you started out with potential energy up here, And all the energy at the start of the problem was the kinetic energy of the bullet, so I can use energy conservation that way. You cannot do that though. The bullet and the block had an inelastic collision. The bullet collided with the block and they stuck together. Remember that only momentum is conserved with an inelastic collision. So I can use energy conservation to go back to the moment right after they started to swing, but I cannot go all the way back to before the inelastic collision. So now I'm going to use momentum conservation to work backwards with this final velocity of the bullet and the block. So this is what I'm doing here. I've got the bullet coming in with some initial velocity that we don't know. The block is a 5 kilogram block with a velocity equal to 0. Okay? So there's the mass of the bullet, and we don't know the velocity of the bullet initial. But then when the bullet and the block are together, we know that the velocity is 0.99 meters per second. Okay? So we can work backwards with an inelastic collision. Momentum initial is equal to momentum final. The initial momentum, the bullet is the only thing that's moving, so 0.002 kilograms multiplied by the initial velocity of the bullet is equal to the final momentum of the bullet and the block together, which was 5.002 kilograms multiplied by 0.99 meters per second. And so I get that the initial velocity of the bullet is a little ridiculous, but it's 2,475.99 meters per second. Now, that's obviously way too fast for a bullet, but I wanted to make these numbers work and kind of give you some visualization here. The bullet and block are not going to swing that far up. It's just not going to happen, okay, unless the bullet is going at supersonic speeds right now. But the way we solved this thing was to work backwards with energy conservation to the point where the bullet and the block interacted with each other. Then we can say energy conservation happened. But I can't go all the way backwards from starting here with potential energy back to all the energy inside the bullet. Can't do it because the bullet and the block had an inelastic collision. So the inelastic collision takes care of the momentum conservation. The energy conservation comes afterward as we swing up with kinetic energy into potential energy. Okay? Be sure to watch this video a couple times if you're really struggling with this concept. But it is important to remember, the inelastic collision, only momentum is conserved. Do not work too far backwards when it comes to the energy conservation. Okay?